Hello everyone, I'm Yu Yuanping from the University of Chinese Academy of Science. Today, I'm glad to share my recent work, HTFuzz, Heap Operation Sequence Sensitive Fuzzing. It's a joint work done by a group of researchers from the University of Chinese Academy of Science and Tsinghua, as well as Zhongguancun Lab Research Institute. Memory corruptions remain a significant threat to software system. Heap-based temporal availability in this work. It means use after free, double free, and null-point dereference is one of the most common type of memory corruptions. To better understand them, we show their occurrence process in the figure. The y-axis is the basic block ID, and the x-axis represents the time. Thus, the blue line in the figure represents the executed heap operation sequence, and the orange block represents the heap memory stage which changes with the heap operations, including malloc and free. In this case, the two blue circled axes means the same memory access operations executed twice. The crash happens as the second one, as the accessed memory is unsafely freed, while the first one is normal. Thus, awareness of the heap operation sequence is the key to find heap-based temporal availability. Fuzzing is a widely utilized technique to find memory corruptions, and graybox fuzzing is the most popular one. In general, they share the workflow of guiding fuzzing process with feedback extracted from program execution. They first execute the mutated test cases and record the execution information such as code coverage feedback. Then, they judge whether the test cases are interesting to save to the sequence according to the feedback. After that, they select more valuable one to optimize the sequence for mutation. Finally, they mutate the seeds using different strategies to generate test cases. The fuzzer will run step 1 to step 4 continuously until the fuzzer stops them. Existing graybox fuzzer in general rely on code coverage feedback to get the fuzzing campaign. For instance, FL use code coverage feedback to explore more codes, while tortoise fuzz and encode try to explore more error-prone operations as additional feedback metrics. They are insufficient for finding heap-based temporal vulnerability. Researchers have proposed several solutions to take into account heap operation sequence during fuzzing. They in general rely on prior knowledge or statistical analysis to recognize candidate vulnerable operations, and they guide the fuzzer to conduct a direct style fuzzing to explore such operations such as UAFL. However, this solution relies on either expert knowledge or imprecise statistical analysis and thus have limitations in practice. This is a motivating example of a use after free vulnerability extracted from a real-world program MP4 box and its dynamic core graph. Its occurrence involves 3 steps. First, the execution begins at main function and arrives at function 1 to generate a heap memory object. Second, in the subsequent execution, function 2 is invoked and it calls function 3 to release the heap memory object. At last, the crash happens as the second use in function 3 when accessing the unsafely released heap memory object. It is noticed that the first use of the allocated heap memory object is normal, but after the function pointer in function 3 points to free and unsafely release the heap memory object. Thus, the second use of it results in a use after free issue and may crash. Current general gray-box fuzzing take code coverage feedback to guide fuzzing is not a good choice for heap-based temporal availability as it ignores the timeline information. Take the AFL for example. Two seeds with the same code coverage are generated while fuzzing. The seed 2 with dangling pointer will be discarded, although it's more valuable. Current specific fuzzing for UAF heavily relies on the candidate sequence as targets to guide fuzzing. However, extracting candidate sequence is limited by prior knowledge or statistical analysis because sequences are easily broken and missed due to the open challenge of statistical analysis such as alias analysis. In the motivation example, it's hard to decide where the function pointer will point to before running, thus leaving out some valuable heap operation sequences. In this paper, we propose a novel heap operation sequence sensitive fuzzing solution, HTFuzz, to increase the diversity of heap operation sequence rather than focus on employing a limited set of candidate operation sequences. We designed HTFuzz and implement it on the popular gray-box fuzzing tool, AFL, which follows the same workflow but comes with improvements in 3 parts. For the first one, we introduced the new heap operation sequence feedback by recording the latest heap operations and save test cases that contribute either to code coverage or heap operation sequence coverage to explore more heap operation sequence via fuzzing. For the second one, we modify the seed selection module to prioritize seeds with more pointers accessed to increase the diversity of pointer alias and the probability of potential bugs. For the third one, we introduce heap operation sequence information in seed mutation to balance both code coverage and the sequence coverage. So, to accomplish such a solution, here comes 3 research questions for us to address. How to deal with the overhead of getting heap operation sequence feedback? How to be sensitive to point alias? How to coordinate with code coverage feedback? Heap operation sequence feedback is the basis of saving, selecting, and mutating seeds in fuzzing. As fine-grained analysis method brings an extremely high overhead and seriously slow down the fuzzing throughput, we choose to track coarse-grained heap operation, such as malloc and free. This is a heap operation sequence of malloc, free, and memo access. We first denote heap operations with binary number 1 for malloc and 0 for free to save the recording space. Then, we track the latest heap operations with a ring buffer 3 of length. Finally, we encode the binary subsequence ring buffer to a decimal number and then save it into a new sequence map. Use the memory access operation location as the index. Thus, the whole bitmap approximately records the heap operation sequence feedback during fuzzing. We use it to save interesting seeds. In addition to heap operation sequence feedback, the diversity of pointer alias is another critical factor for finding heap-based temporal availabilities. As fine-grained analysis method brings an extremely high overhead, we statically identify the instructions related to point and alias access to count their frequency in the execution. As seed selection design for fuzzing throughput may harm diversity of pointer alias, we prioritize seeds with larger access count as favored and get selected to mutate with a higher probability by the fuzzer. Well-organized seed mutation is helpful to offer abundant candidate test case for heap-based temporal availability. Simply combining heap operation sequence feedback with code coverage feedback together will cause conflicts. As AFL use effector map to identify interesting bytes that contribute to code coverage and skip mutating other bytes, which may harm the seeds that only result in new heap operation sequence. We chose to upgrade the identification algorithm of effector map. As the efficiency of mutation operators vary greatly, we reference MOPT to schedule mutation strategies based on heap operation sequence feedback besides the original code coverage feedback. During our evaluation, we will answer the questions of HTFuzz with its effectiveness in finding real-world heap-based temporal availability, or improvements contribute to its efficiency and it outperforms the baseline fuzzers. Here are our evaluation setup. We first evaluate the effectiveness of HTFuzz in finding real-world vulnerabilities. We found 92 vulnerability totally in the benchmark applications, including 74 heap-based temporal vulnerabilities, and we got 37 new CVEs assigned. According to the number of heap-based temporal vulnerability found as time flow, we can see that nearly half of the vulnerability are discovered within 10 hours. We then compare the number of vulnerabilities found with other fuzzers. The result shows that HTFuzz outperforms all the baseline in terms of real-world vulnerability discovery, including the total number of the heap-based temporal vulnerabilities. As we have to set the ring buffer length and the sequence bitmap size, we first perform a study of different settings by comparing the fuzzing performance. Considering the bitmap density and the bug number, we get the bitmap size to 16 and the length to 3 as the default setting of HTFuzz. Then, we evaluate the ablation studies of 3 fuzzing strategy modifications, and the results show that all improvements are positive to the effectiveness of HTFuzz. In the following, we compare HTFuzz with the dataset of UAFL and UEFuzz and reproduce all the reported UEF and double-free vulnerabilities. In addition, we found 7 previously missed UEF vulnerabilities. We also compare HTFuzz with 9 general graybox fuzzers. HTFuzz is more capable of discovering heap-based temporal vulnerability according to the total and the average number. Based on the p-value and of the memory union U-test, it outperforms all the baseline fuzzers. Then, we evaluate the amount of heap operation sequence found by different fuzzers, and the result shows HTFuzz found much more than baseline fuzzers. In our evaluation, as HTFuzz has to configure the recording bitmap size and the ring buffer length, we cannot ensure the default setting is the best. We recommend adjusting hyperparameter based on the available computing resource adaptively. It's hard to evaluate the capability of fuzzers, including the testing randomness and the benchmark bias. We test the newly published datasets, and each experiment is done long and multi times, and we also do memory union U-test for the static analysis of HTFuzz. We believe that the result of HTFuzz is representative. In the end, we summarize our work. Thank you for your listening.